So now that we have defined this idea of gradient, this additional way to do a spatial derivative in 3 dimensions, let's talk about how that connects to something called electric potential or voltage. All right. And so the relationship itself is pretty simple. It's that the gradient of some scalar valued electric potential called V, and this is electric potential, equals the negative of the electric field. All right. And remember, we're implying that the following is true, that the closed integral along a path of E dot dl equals 0. This must be true, which is true for static cases. Right, so this is true if nothing is changing with time. Right, so if nothing is changing with time, which is what we call statics, then it is possible to find a value V everywhere such that you can take the gradient of this V after you've defined it, and you will immediately figure out what the electric field is. So we can almost, this is a neat trick because keeping track of electric fields everywhere is complicated. There's 3 different numbers to it, right? Everywhere I have an electric field, it's got an X, Y, and Z component. How do I keep track of that? Well, it'd be much simpler if we could just have a single number with every single location, right? Just like temperature. It's easier to keep track of the temperature as a function of space than it is to keep track of the wind speed and velocity and direction. And if we keep track of temperature, in this case, electric potential, all we got to do is take the gradient, and then we know what the electric field is. And so that sort of greatly simplifies the problem. All right. So this sort of gives us a new way to think about what electric field is. Right. We thought about electric fields as being force per charge. And that kind of made sense, but the real units for electric field is volts per meter. So let's unpack that for a second. All right, volts is the unit of electric potential. Right, so it's potential energy per charge. Right, so when we take the gradient, right, the gradient is defined with spatial derivatives in it. Right, here's our definition of the gradient. The gradient has spatial derivatives, ddx, ddy, and ddz in it, which means that the units of the gradient would have a per meter compared to the original quantity itself. So if the vector v is electric potential or energy per charge, then the units of electric field is going to be volts per meter, right? Where energy per charge, we're calling that volt. So that's why the electric field is volts per meter, because we can think of it as a rate of change of potential, right? So E is the rate of change of potential energy. Right, it's the rate of change of the voltage or the electric potential. All right, so what this means is that, and let me just box this so we can know that this is important. All right, what that means is that if the electric field is pointed this way, right, and I've got points A and points B, and let's say they're separated by 1 meter, then if I walk in the direction of the electric field, the potential is going to change by that number of volts. So if E is, let's say it's 10 volts per meter, then as we walk from A to B, V will decrease by 10 volts. Right, it will decrease by 10 volts from A to B, the electric potential of any charge at location A. If you slide it to location B, it's going to lose about 10 volts of potential. But let's unpack this for a second, because we've got this gradient and we've got the E, right? And now we're reinterpreting E as a rate of change of the gradient. But why this minus sign, right? So think about what the electric field is going to do. So the electric field is causing a decrease in the potential. And it's much like you're taking a charge and you're pulling it downhill. If you're pulling the charge downhill, then you're reducing its potential energy. And so the electric field actually points in the direction of decreasing potential, right? So E is the direction of decreasing potential. And since the gradient is technically the direction of the increasing potential, we've got to put that minus sign to flip it around. All right. So in the notes, I've got the details on how you calculate the potential from a single charge, or from a distribution of charge, or from a line of charge, or a surface of charge. I'll briefly show just one example, and I'll refer you to the notes to see the details. It's very much like Coulomb's law in the way we had a Coulomb's law for a single point charge and a Coulomb's law for a line of charge, or a surface of charge. But I'll just write down that the potential from one charge is going to go like this, right? The voltage as a function of R equals Q over 4 pi epsilon R, where R is the distance from that charge. Q is the amount of charge that's present. And epsilon is the permittivity. Right, so as you are walking away from a positive charge and R increases, the electric potential at your location is going to decrease as 1 over R. Right, and inside the notes, you'll see what this is for a line and a volume charge as well. All right. Now, even though we've got these relationships, this one and the equivalent one for line and surface and volumes of charges, that's not all that useful in general, because we basically can't take measurements at infinitely tight spacing, right? We can't know this everywhere. And so we're going to talk about in the next lecture a numerical way to actually apply this notion of gradient that works for practical scenarios.